Okay, very good afternoon to all of you. So it's a very tough time of the day to have a class, and also it's an online class. So my name is Dr. Susi from IMEN. So earlier in the day, in the morning, you heard from Dr. D and also Prof. Pankaj. So Prof. Pankaj spoke on waveguides and Dr. D on Maxwell equations. Okay. So this afternoon, I will continue with optoelectronic devices at low scale dimension. So there are supposed to be, let me see, 13 students in the class. So far 11 of you have joined. So there's two more people who have not joined, Muhammad Pomad and Rahmat Zaki. So we'll go ahead and start and I hope they both will join the class later on. Okay. So my slides are already in UCAM folio and also in the Teams as well. So I hope all of you have the slides, and if you have any questions while I'm presenting, just you can raise your hand over here, or you put your question in the chat, and then once the session or the class is over, then I'll answer all your questions. Okay, so feel free to stop me if you don't understand anything. And if I speak in Malay, is it fine? Everyone understands Malay here? Semua faham bahasa Melayu?
Yes. Faham, Doktor.
Faham, Doktor.
Anyone wants the session to be in English? I think we have one foreign student.
Ada international student.
Siapa Dilip
Dilip, lepas tu Muhammad Poman tu kot.
Oh ya ke, diorang foreigner lah, okay. So kalau saya continue bahasa Inggeris, lepas tu kalau ada yang tak faham tanya je lah
Alright.
Okay. Alright, I think I'll go ahead and start. Okay. So this is lecture 7, Nanoscale Optoelectronic Devices. Okay, my name is Susi from IMEN. So just a brief background. I'm a product of UKM. I did my Bachelor of Engineering, and then I had a short stint with Intel Products as a product NPI engineer. I continued with my master's in UKM and also my PhD. And then I've been in IMEN since 2009 onwards. So currently I'm co-supervising 6 MSc have completed, 18 PhD have completed, 4 PhD ongoing and 3 master student ongoing. So I'm an author, co-author of 2 book chapters, more than 180 Scopus ISI journals and proceedings. So currently my research projects are in plasmonics, quantum electronics, nanophotonics, biophotonics, optoelectrochemical sensors, and some other work that I've done in the past are like silicon, germanium, indium gas, quantum dot, PIN photodiodes. Also development of multi-quantum well, long wavelength, vertical cavity surface emitting lasers. Also high-K material in nanoscale MOSFET. This is a type of a transistor. And semiconductor optical amplifier in CWDM wavelength. Also, I have students who have worked on silicon on insulator based micro ring resonators. These are like splitters in optical devices, also Mach-Zehnder interferometers. So these are my expertise in nanophotonics, SPR based nanosensors, optical fiber based and also waveguide based. Also fabrication and characterization of optoelectronic devices using spin-on diffusion. Finite element method based numerical analysis using Silvaco, numerical and also COMSOL. And in terms of statistical optimization, my expertise is in fractional factorial design and also in Taguchi method. So just a short advertisement, I'm seeking for masters and PhD students for plasmonics based projects. So if you have any contacts or friends who are interested, you can ask them to drop me an email at susi@ukm.edu.my. Okay? Alright, so we move on to the actual lecture. Alright, optoelectronics is a study on electronic devices that interact with light. So interact means either it emits or it absorbs, right? Detect. or you can modulate the signal or even switch it. And light is any type of electromagnetic radiation. Okay, so basically electromagnetic radiation, one of the example is light. Okay, electronic usually means made of semiconductors. Emerging technologies are such as plasmonics, graphene, plasmonics, graphene, carbon nanotubes, phosphorine, silicon, uh, silicene, this should be silicene, hexagonal boron nitride, and also molecular devices. Okay, so the interplay between quantum electronics, nonlinear optics, physics of semiconductors, and transport phenomena. So all this constitutes optoelectronics. So it's important not to get lost and see the coherence and connections between the different subjects. Okay, so this a lot of things here: quantum electronics, nonlinear optics, physics of semiconductors, and also transport phenomena. Okay, so in optoelectronics, the main devices are semiconductor lasers and also LED, which will be covered in this lecture. Also detectors and solar cells. Okay, so I think there's one student from Surrey who's in this lecture today. So, but I haven't got much information on solar cell, just a basic theoretical knowledge about solar cells. Okay, and also some papers related to perovskite solar cells. And nonlinear optical systems will not be covered in this lecture. And some novel devices currently are carbon-based devices and also plasmonic-based devices. So in this lecture, I will cover the basic principles and also the device physics. And I'll give you some example of state-of-the-art devices and also the challenges and outlook for the future. So integrated photonics, nano devices, quantum optical systems, for example, cryptography, communications, and now you have IR 4.0. So all these applications in mind, but you must remember the basic physics of it. All right, the application may be many, but basically the physics is similar or the same. Okay. So as you are all well aware, the nature of light is given by this electromagnetic spectrum equation, where E is equals to Hc over lambda. E is the photon energy in joules. H is the Planck's constant given by 6.6 times 10 to the power minus 34 joule seconds. C is the speed of light given by this value. Normally we use 3 times 10 to the power of 8 meter per second. And lambda is the wavelength. Is the wavelength of light in meters, and it's also equivalent to C over F, which C is actually the speed of light and F is the frequency in free space. And 1 electron volt is given by 1.6 times 10 to the power of 19 joule. Okay, so as you can see here, there are many classes of the electromagnetic spectrum. So it covers from the gamma right until the extremely low frequency. So you can see for the gamma ray, it is the frequency can be as high as 300 etahertz. And this is equivalent to 1 picometer of wavelength. And the equivalent energy is also very high, 1.24 mega electron volts. And as you go down this table, you can see that the frequency reduces, okay? And as well as the energy, it reduces, okay? From mega electron volts, it goes down until femto electron volts. And the equivalent wavelength increases. So frequency and wavelength, they are always opposite, right? As you can see from here, right? They are always in the opposite, the frequency and also the wavelength from here, right? Lambda and F, they are in the opposite. So if this is in increasing trend, this will be in decreasing trend. Okay. So the visible light spectrum from the whole list of electromagnetic spectrum, the visible light spectrum occupies only a small portion of the overall electromagnetic spectrum. So this is from 400 nanometer to 700 nanometer, thus just this small region over here. And we are interested primarily in the visible light region and the regions just above, which is the ultraviolet, and also just below, which is the infrared. And why are we interested in these three regions, ultraviolet, visible, and infrared? Simply because it is easy to make devices that can generate these kinds of light and also to detect these kinds of lights. Okay, so that's why the emphasis will be in ultraviolet, visible, and also in infrared. Okay, this is just for your information, the effect of the electromagnetic spectrum and also radiation. How is our exposure to radiation on the electromagnetic spectrum? So you can see here, if you're using a computer, the radiation is quite low, all right? But as you move on using other kinds of application which uses other parts of the spectrum, radio, cell phone, microwave, remote control, this is the visible light. And as you go up to higher radiation or higher wavelength or higher frequency, which is ultraviolet, X-rays, and also gamma rays, you can see that the radiation increases, okay? And for the regions over here, these are non-ionizing radiation where it's traditionally perceived as harmless due to its lack of potency. But when you're exposed to higher frequency spectrum, you are exposed to ionizing radiation where it can cause cellular or DNA damage with prolonged exposure. So this is just some information for you. So you need to control the amount of time exposed to UV, X-rays, and also gamma rays. Okay. All right. In terms of optical devices, the human eye is sensitive to light with HV less than 0.7 micrometer, which is equivalent to higher than 1.8 electron volts. So as you can see here, this is our eye response, okay? So we can see red, orange, yellow, green, blue, and violet. This is the colors of the rainbow. We can see these colors, but your eyes cannot detect or you cannot see infrared and also ultraviolet. And what are the materials within this visible region? What materials are normally used to create these colors? Some examples are gallium phosphide, cadmium selenide, cadmium sulfide, all right? And for infrared, some of the semiconductor materials which are normally used are silicon and also gallium arsenide. And for ultraviolet is gallium nitride and also zinc sulfide, okay? And if you look at this table over here, it shows the band gap energy versus the lattice constant. And there are three main substrates here, which is the gallium arsenide, indium phosphide, and also gallium antimony. And you can see here the band gap energy changes, all right, when you change the molarity of the materials inside each one of these substrates. Okay, for example, in gallium arsenide, when you add indium and arsenide, okay, for example, gallium arsenide is over here. And when you add a component of indium, the band gap energy drops, okay? And similarly, for indium phosphide, it is right over here. And when you add, or when you, let's see, where does it go? Okay, for example, if you add aluminium, all right, you can increase the band gap energy of indium phosphide. Similarly for the gallium antimony as well. So this is called band gap engineering. By adding and removing atoms inside substrates, we can tailor the band gap to different types of energy. So as you know, different types of energy caters or emits and absorbs different types of wavelength. So this is the method used in engineering to meet or to detect and absorb different wavelengths. Okay. So this is another figure which shows the band gap energy versus lattice constant for elemental and also compound semiconductors. So there are various kinds of material here. So you can see for the visible light over here, some of the common materials used to form to make lasers, LEDs, and also to make detectors, such as zinc selenide, cadmium sulfide, zinc, and so forth over here. And when you go up higher or lower for the band gap energy, different kinds of materials are also used, okay? And it also shows the type of structure. I think in your past lecture, you have learned about the hexagonal structure and also the cubic structure. So all these materials have different structures and they play an effect in the absorption and also in the recombination of carriers inside the device. Okay, so we will first move to light sources. I'll cover two types of light sources, which is the light emitting and the second is the laser. Light amplification by stimulated emission of radiation. It is the short form for laser. And there are basically two lasers, which are gas laser and solid state laser. But in this lecture, I will only cover solid state laser. Okay. All right. So two types of laser, LED and also laser diode. So the materials used are semiconductors, indium gallium phosphide, aluminum gallium arsenide, and InGaAs. So this relationship is very important for you to remember. How do you change the band gap energy versus the wavelength? Suppose you have a material and you know the band gap energy and you want to know what wavelength it absorbs or emits. This is the equation which will be used. So if you simplify it, you replace the Planck's constant and also the speed of light, you get this simplified form where the wavelength is equal to 1.24 divided by the band gap. Okay, so you can interchange and get the equivalent wavelength and also the band gap. So some of the common materials used in lasers are such as listed here. And the wavelength range, you can see this is in the visible wavelength range. So this is the equivalent band gap energy. Gallium arsenide, it is in the infrared. 0.9 is already in the infrared region. So the band gap energy is 1.4 electron volts. Aluminum gallium arsenide also in the infrared. Indium gallium arsenide further on to the infrared, and indium gallium arsenide phosphide also in the infrared. Okay, so these are the equivalent band gap energy. All right, this is another important equation you should remember. So for lasers, electrons recombine with holes to emit photons. All right. So H is the Planck's constant and F is the frequency. All right, C over lambda. And in lasers and also in LED, the electrons and hole recombine to form photon. But in photodetectors, the opposite occur. In photodetector and also in solar cells, the opposite occur. Light is absorbed to form electrons and holes, the opposite direction. So this is a bidirectional equation where when electrons and holes recombine, you get a photon is emitted, all right, this way. If you go the opposite way, when photon is absorbed, electrons and holes are formed in photodetectors and also in solar cells. So if you can understand this simple concept where how carrier recombination can emit photons, and photon absorption can create or make electron and hole pairs. Okay. So in a laser, so this is a circuit for a laser, and it basically comprises of a PN junction. And you can see here, when there are no voltage applied across the PN junction, so you have a very large gap here between the P and N regions. Okay, so the free electrons, they are not free to cross over to the P region. And when we apply a forward voltage, this barrier is reduced and you have a flow of electrons and holes where they recombine, electrons and holes recombine, and you have the emission of a photon. Okay, and that is how that is what we call as a emission, laser emission or a LED emission. Okay, so this shows a heterojunction or a double heterostructure. What it simply means, there are more layers in it. So basically this is the active layer. The active layer is the layer which will emit the photon. So this active layer is, the band gap is 0.95, which is equivalent to emission of 1.3 microns of wavelength. Okay, and it is sandwiched between P and N types of indium phosphide. And you can see here that the band gap is higher over here simply because we want to allow the recombination to occur in the low band gap energy region, okay, in the active layer. And in terms of refractive index, so this is in terms of charge carriers, which is electrons and holes. But in terms of optical effect, you know about the refractive index. Prof. Pankaj have already explained in the past class. So refractive index is basically the speed of material, or the speed of light in a particular material. So you can see here the refractive index is low in the N-indium phosphate and it's high in the active layer. So what this causes is what we call as a photon confinement. You make sure that the photon emitted stays in the active layer in order to aid the stimulation of light. Okay, so basically you have a carrier, or we have electrons and holes confinement, as well as an optical confinement. There are two effects in a both in a detector and also in a laser. You have a carrier confinement and optical confinement. Two effects in order to have light emission. So carrier need to be confined in the active layer, and light also needs to be confined in the active layer for emission to occur. Okay. So this is a band gap energy for aluminum gallium arsenide, and also this is the difference in the aluminum mole fraction, which is over here, the value. So band gap engineering can occur when we change the aluminum mole fraction. Okay. So similarly, when the band gap changes, the wavelength can also be changed. So almost all electronic transitions that occur in atoms involve photons fall into one of three categories. So for spontaneous emission, so as mentioned just now, the recombination of electrons and holes cause the emission of a photon. And you can see here in the before the excited state, the electron stays at the E2 level, all right? And in the ground state, after a supply of voltage, you can see that the electron has recombined with the hole in the E1 level, all right? And the effect, because of conservation of energy, all right, when it moves from a higher energy state to a lower energy state, that energy gets transformed into a photon, all right? And the amount of this photon, as mentioned, is equivalent to the band gap of this E2 minus E1, okay? So for LEDs, the holes and electrons recombine to emit photon, and the energy or wavelength of the emitted light is equivalent to the band gap between the conduction band and valence band. Is it clear so far? Do you understand?
Yes, Doctor.
Clear, Doctor.
Clear, all right. Okay. Just checking, making sure you're not going to sleep. All right, okay, let's move on. Okay. Now, principle of a LED and also a laser is similar. Only thing, a laser, you have an external source to stimulate the recombination, whereas in an LED there is no external stimulation. So this is similar like the graph just now. Without the supply of voltage, you have a high barrier here between the P and N regions, and electrons and holes cannot flow freely. But when it's forward bias, you can see that the barrier is reduced and electrons recombine with the holes in the active region, which is P gallium arsenide, and due to conservation of energy, the electrons recombine with the holes and light is emitted as another form of energy. Okay, and again we can tailor this recombination or the emitted light based on doping. All right, you can dope it with various kinds of materials, and dope, aluminum dope, and you can shift the band gap energy accordingly. All right. This just shows different materials for different wavelength. So basically for this near infrared is gallium arsenide phosphate and aluminum gallium arsenide. And for longer infrared, these are all the materials which are used. For visible light, normally indium gallium nitride, silicon carbide are normally used, and also gallium phosphate and gallium arsenide with addition of phosphide a bit here for orange. Okay. So different kinds of, okay. So an LED is actually a chip. It is a semiconducting material, and you have a PN junction. So when it's forward bias, charge carriers, they flow into the junction, the electron meets a hole, and it falls into a lower energy level and releases energy in the form of a photon. So the wavelength of the light emitted and therefore its color depends on the band gap energy of the materials forming the PN junction. So in indirect band gap materials, okay, I think in whose class you have learned about Prof. Yusri's class, you have learned about band gap, right?
Yes, Doctor.
Okay, you have learned about direct and indirect band gap materials. So silicon and germanium are indirect band gap materials, and the electrons and holes recombine using non-radiative transition. So therefore, it produces no optical emission. All right, there is no optical emission in silicon and germanium. That's why you cannot find silicon and germanium lasers. All right, because it's a indirect band gap material. In order for emission to occur, it must be a direct band gap material. But currently, research is going on to tailor or to modify silicon such that it can also emit. All right, we do band gap engineering and defect engineering in silicon so that it can emit light. All right, by adding impurities and so forth. Okay, so these are images of different kinds of LEDs. And the materials used for LED have a direct band gap with energies corresponding to near infrared, visible or near ultraviolet light. Okay, so it's a similar figure as just now. Recombination and light is emitted. Okay, so the next few slides, I'm going to skip it because I find it similar to what Dr. Yusri has explained, is the band structure of intrinsic semiconductors. So my apology for the overlapping slides. Okay, I just noticed it just now. So anyway, I'll skip this band structure. So basically, electrons and holes, they are in a Bohr model. And you know just now when electrons, they recombine, so they move to a lower energy level. So when they move to a lower energy level, light can be emitted in other forms of energy such as photon. Okay. All right, so this is a normal schematic for a conduction band and valence band. But actually it is not a straight line, it is actually a curvature. And this is direct band gap, and this is direct band gap semiconductor. And this is indirect, for example, silicon and also germanium, where you can see that the minimum of the conduction band is not in line with the maximum of the valence band. So in defect engineering for silicon, they move this band gap, or maybe they have an intermediate band gap. So it moves here and then it moves here. So you can make silicon into a laser as well using defect engineering. Okay. We move on to compound semiconductors. These are 3,5 and also 2,6 compounds. And semiconductor like gallium arsenide, the doping can be accomplished by varying the stoichiometry, which is the ratio of the gallium atoms to the arsenide atoms. So a slight increase in the proportion of arsenide produces N-type doping, and if you increase the gallium, you get a P-type doping. Okay. So these are different types of material, semiconductor, compound semiconductor materials included, and the type of the band gap, whether direct or indirect, and the corresponding band gap energy. All right. So, so depending on what kind of LED or laser that you're trying to produce, you have to use the correct materials. Okay. All right, let's zoom in and look into the anatomy of a LED. So basically, in terms of a semiconductor device, you have a silicon substrate, just as a substrate. And you have the P layers, which is made from germanium, all right? And also the N layers, also made of germanium. And you can see that this is the back contact, and this is the signal contact. One is for the cathode, one is for the anode. And light is emitted at the surface. Okay, this is a normal chip that you see, the LED chip, and it comprises of an anode and also a cathode. And if you notice here, the flat spot is near to the cathode. Okay, and this is the chip. This chip over here is exactly here, the semiconductor die. And else than that, you have a wire bond to bond the anode and the cathodes, and then you have a reflective cavity. You also have the anvil for the lead frame over here. And at the top here is the epoxy lens or the casing. All right. So if you notice for a LED, you have a long leg for the anode, and the cathode is actually a shorter leg. All right. So the way to differentiate a cathode is it has a flat spot and the leg is shorter. Okay. So this is the signage for LED, and this shows more detail of the bonding wire. All right, of the semiconductor chip over here. And you can see light is being emitted out from the surface of the LED, and so these emitted lights will hit the epoxy lens or the case over here. This is an actual fabricated LED. All right, this is the BL contact over here, and this is the signal contact over here. So this is the surface of the LED chip. Okay. So LEDs are usually built on an N-type substrate. It has electrodes attached to the P-type layer deposited on its surface. And the refractive index of the packaged material should match the index of the semiconductor. Okay. What this means is so you have the refractive index of the semiconductor. It should match with its packaging material, with whatever is above here. All right. And why? This is because the produced light gets partially reflected back into the semiconductor, where it may be absorbed and turned into additional heat, thus lowering the efficiency. So you can see here when light is emitted out, if you do not select the correct material over here, it can get reflected back and it is generated as heat inside the semiconductor chip. And it can lower the efficiency of the LED. So the refractive index of a material is the ratio of the speed of light in vacuum to the speed of light in the material. So this type of reflection also occurs at the surface of the package if the LED is coupled to a medium with a different refractive index, such as a glass fiber or air. So there are two issues here in an LED. The first is the chip and the material packaging it. And the second is with the dome or the lens, because then light will need to be emitted out. So selection of the material of the dome is also very important, so light does not get reflected back in. Then you will not get a very bright LED. So the reflection is most commonly reduced by using a dome shape, a half sphere package with the diode in the center, so that the outgoing light strikes the surface perpendicularly, at which angle the reflection is minimized. So if you can see here, LEDs always have a dome shape. So the reason for this is so that light hits it perpendicularly. So when light hits it perpendicularly, it minimizes reflection and also refraction. Okay, based on Snell's law. So that's why it's dome shaped, to reduce the reflection and refraction. Okay, this type of reflection also occurs at the surface of the package if the LED is coupled. All right, I'm done with this. Okay, the refractive index of most LED semiconductors is quite high. All right, 3.7 the refractive index. So always, in almost all cases, it is coupled to a much lower index medium. That means lower than 3.7. All right, this is for optical confinement. So the large index difference makes the reflection quite substantial, and this is usually one of the dominant causes of LED inefficiency. So light gets refracted and reflected because you have high refractive index and low refractive index, so it gets lost. Okay. Often, more than half of the emitted light is reflected back at the LED package or package air. LED package and package air. All right, LED package and package air. So light lost here and light lost here. So in the end, you get very inefficient LED. Okay. All right, and the way to overcome this is the dome-shaped package. All right, and also using an anti-reflection coating to reduce the loss of light. Okay. So basically, this is just a description of Snell's law. So basically, when you have an incident light at an angle, so light will get reflected or refracted. But if it's perpendicular, all right, you can see that it just goes through. So that is the reason for the dome shape. So when it's a dome shape, the light hits it perpendicularly. So there is minimal light which is reflected or refracted. Okay. Okay. So conventional LEDs are made from a variety of inorganic semiconductor materials producing the following colors. All right. So now the most famous is blue light, for which a Nobel Prize was obtained by the researchers. So it is made from indium gallium nitride, which lasers at 450 to 470 nanometer. And there are also substrates, silicon carbide is also used for blue light, sapphire, and so forth. Okay. All right. If the emitting layer, just now we looked at semiconducting materials, right? We looked at compound semiconductor materials. Now, what if the emitting layer is made out of organic compound? So then it is known as an organic light emitting diode. In fact, Dr. Yusri has also covered this organic electronics. But I'll just go through quickly, just some rough information. So to function as a semiconductor, the organic emitting material must have a specific bonding structure. So the emitting material can be a small organic molecule in a crystalline phase or a polymer. Polymer materials, which are becoming very famous now, they can be used to make polymer LEDs or flexible LEDs, right? Okay. So this is a comparison between a LED screen or a LCD screen, liquid crystal display, versus an OLED, organic LED. All right. So OLEDs, they can be used to make digital displays in television, in screens, in computer monitors, also in your smartphones, in your handheld game console, and also your PDA. And the current major research is the development of white OLED devices for use in solid state lighting. Okay, so basically this is a substrate. This is the structure of the OLED. So you have the anode and the cathode, but now you can see that the semiconductor material is replaced with organic molecule or polymer, or for the conductive layer and also for the emissive layer. All right, it's replaced with organic material. And in comparison with OLED versus a LED, you can see here in an LED, it is a complex structure because you have the backlight over here and you need a lighting unit. It's a pixel unit. You can see in terms of layers, there are many layers required for a LED television. Whereas for an OLED, the structure is simple. It is self-emissive and the lighting unit is also pixel unit. And you can see it comprises a minimal layer. Okay. So, it also emits the same amount of light, but here is thicker, here is thinner. This is the major difference. And polymer LED, which is a flexible LED, it is lightweight and flexible, so they can be made as thin films. They have extraordinary resolution. They can be seen from any angle without loss of information, enable more energy efficiency, consume less power. They can be used to make flexible displays, and they offer high brightness at low drive voltages, and they ensure glare-free viewing. Okay, so basically the active region is replaced with a polymer material. Okay. All right, this is a comparison of smartphone display technology. BlackBerry, HTC One, iPhone 5, Lumia, and also Galaxy. So basically looking at the type of technology used. So some are using LCD and AMOLED, right? Amorphous LED. And here it shows the foldable display generation. Okay, you have the first generation, you only can fold two sides. Outfolding, you call it outfolding. And then we move on to second generation, infolding. Okay, this was released in Q4 of 2019. And then we have infolding, the third generation. Okay, the third generation is infolding. And now in the fourth generation, I think it's already out or what, I'm not sure. You have multiple folding in and out. You can, it's like a paper. You can fold multiple ways that you want. Okay, flexible smartphone. Okay, so TFT basically means thin film transistor. LCD is liquid crystal display. Okay, and so as you can see, the technology of flexible displays is becoming very, very famous now. Okay, so that's all for LED. I'm going to move on to lasers now. So any questions on LED? Hello? Any questions?
No, doctor.
We are clear.
All
Clear,
clear?
clear.
All
All clear.
understand? Oh, are you guys sleeping?
No, no, doctor.
Of course, not the press.
Okay,
All
so
clear,
it's good
doctor.
to see that all of you able to join. All right, thank you for joining. I know it's a very hard time. It's in the afternoon. It's normally the napping time, right? And it's a heavy subject, lasers and LED. Okay, all right, let's move on. Okay, we'll move on. Next, we move on to lasers. Okay, a typical laser, it emits light in a narrow, low divergence monochromatic beam. Okay, so basically it's the same. You have an anode and a cathode and you have a gain medium. The only thing difference from an LED is you have a very thin or a very sharp beam compared to a laser, LED, all right? So in contrast to a light source, for example, an incandescent light bulb, it emits over a wide area and over a wide spectrum of wavelengths. So laser consists of a gain medium.
Excuse me, doctor.
And this gain medium is, yes. Someone said something? Did someone say something? Okay, no, I'll just move on. Okay, right. Okay, so there's a optical cavity and it is to supply energy to the gain medium. All right, so this gain medium, it can be a gas. All right, it can be a gas, a liquid, a solid, or a free electron with appropriate optical properties. Okay. All right, I know it's a lot of words, but sometimes it's easy to read and make you all understand rather than explaining it from figures. So it's a cavity. It consists of two mirrors. Okay, so there are two mirrors over here. There's a front mirror and a back mirror. There's a front mirror and also a back mirror. Okay, so the light bounces back and forth each time passing through the gain medium. So what happens here is a photon is formed in the gain medium and then it's emitted. Then it sees this mirror, it gets reflected back. Then it sees this mirror, it gets reflected back and forth, back and forth. Each time when the photon meets the active region, another photon gets emitted. So it multiplies. It's an amplifier. So light gets amplified over here. And this amplification occurs non-stop until a certain amount of light escapes through the opening in the front reflector. This front reflector has got a small opening with a, it is not 100% reflecting, whereas the back reflector is 100% reflecting. So when it achieves enough power or momentum to emit out, so a light beam is formed. Okay. So one of the two mirrors, the output coupler or the front reflector, it is partially transparent. So the output laser beam is emitted through this mirror. So light of a specific wavelength that passes through the gain medium is amplified, simply meaning it is increased in power. The surrounding mirrors ensure that most of the light makes many passes through the gain medium, stimulating the gain material continuously. Part of the light that is between the mirrors, that is within the cavity, passes through the partially transparent mirror and escapes as a beam of light. As what I explained just now, light just passes through, you know, it's like oscillating in this gain medium until it gains enough power to be emitted. Okay, the process of supplying the energy required for the amplification is called pumping. You have an external pumping. It can be an electrical current supplying voltage or current, or it can be an optical pumping, another optical source pumping it. So in this lecture, I only consider injection pumping, which is current or voltage pumping. So you have a pump it pumps up the electrons to a higher energy level. And the first radiation is radiationless transition. It goes down to a lower energy due to conservation of energy, and then it goes down to level 1 to recombine. All right, and here you have a laser transition. Okay. 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 Right. Okay. So it's an active medium with a semiconductor similar to a LED, and the most common and practical type is using a PN junction, and then you have an injected electrical current, a forward bias, and sometimes we refer to them as injection laser diodes to distinguish them from optically pumped laser diodes. Okay, so it's a similar figure as the LED. So you have in equilibrium band structure the high barrier over here, and upon supply of a forward bias, this barrier is reduced and electrons and holes recombine in the active region, and you have emission of a photon. All right, similar as in LED. Okay, but the difference is the difference between LED and LD is in a laser diode you have optical pumping, optical or electrical pumping, right? There's an external pumping, as what I showed you just now. You have electrical pumping over here. In a LED, you do not have this external pumping. So in a laser, it's called stimulated emission. This emission is stimulated because you pump it. In a LED, it is called spontaneous emission. No external pumping is given. Okay. All right. So this shows a striped laser schematic. You can see that it's almost similar to the LED. Only thing, different materials, of course, and also the structure. You have the emitting region over here. For the LED, it is a surface emitting, but for laser, it can be edge emitting, you know, like when you're using it in your laser pointer, it's an edge emitting laser. All right. So you have P region and you have N region, and this is the active region where light is emitted. So the challenge is to make sure that electrons and holes, they move to this region. They must move to the active region for recombination. And when photon is emitted, the challenge is to make sure the photon stays in this region without going into other region, because you need amplification to occur here so that emission can occur. Okay, let's look at a simple example of recombination. Okay, let's look at the amount or the number of carriers recombining. All right, this is given by dn dt. N is the carrier versus time. All right, and the number of carriers is determined by the charge carriers n times with the volume of the cavity or the active region. All right, versus time. And this is given by volume times with dn dt, and the volume simply means, for example, if the structure is volume is given by L times L, the height and the width, times with the length. Let's look at the active region alone, the D. So L times D gives the volume. Okay, the number of electrons entering is given by the current I divided by the electron, and the dn dt is about 10 to the power of 24 electron hole pairs. In any given time, you have 10 to the power of 24 electron hole pairs. So the amount of current is equivalent to volume times the rate of charge carrier movement. So this is current density. If you current density is given by I divided by L2, so you bring this L down. So this is current density, E times D times dn dt, which gives you a current density of 10 kiloampere per centimeter squared for an active length of 1 micron. All right, so for 1 micron, the amount of current is 10 kiloampere per centimeter squared. In the subsequent slide later on, we will see what will happen when we reduce this to 1 nanometer, right, to look at quantum effects. So the amount of current will be reduced, but how do we cater for the reduction in K? This is a laser diode construction. Basically, it has a P and N type layer, and this is the active region. You have a metal contact, right? And as in other lasers, I don't know how to take this down because you cannot see the bottom part. I don't know how to do this. Anyway, so the gain region is surrounded with an optical cavity to form a laser. All right, so this is the optical cavity. And in the simplest form of laser diode, an optical that is made on the crystal structure, such as the light is confined in a relatively narrow line. So this is just repeating what I've mentioned just now. So the photon is emitted and it moves inside the active region because this is a high refractive index material. These are low. So you know from Snell's law that when you have total internal reflection, the refractive index over here is low, the refractive index over here is high. So light is confinement of light. And as the light wave passes through the cavity, it is amplified by stimulated emission, but light is also lost due to absorption and by incomplete reflection. So when there is more amplification than loss, the diode begins to laze. It lasers out over here. Okay. So the important property of laser diode is determined by the geometry of the optical cavity. And in the vertical direction, the light is confined in a very thin layer. And the structure supports only a single optical mode. But you can also have multi-mode. Alright? Alright, so this is single mode. You only have one mode of light, single wavelength. But you can also have multi-mode, multi-wavelength. You can see here for a single mode is very sharp. This is the light intensity is very sharp and the diameter is very small. For example, it's a laser pointer. Alright, it's very sharp. And the multi-mode, example of a multi-mode is a LED. There are multi-wavelengths in it, and you can see that the light is spread out over a wide range of wavelengths, and also the diameter is also big. So single mode is laser pointer and also in fiber optics. And multiple wavelength laser, normally we use it for harmonics of the fundamental. Okay, so this is the main emitted wavelength. All right, this is the main maximum gain occurs here. You also have what we call side modes. These are side, and in laser diodes, such as most visible lasers, they operate at a single wavelength, but that wavelength is unstable and it changes due to fluctuations in current or temperature. So this wavelength can also change because of temperature effect. And in terms of diffraction, the beam diverges. So when it leaves, this is a laser pointer. So when it leaves, you can see that the light begins to diverge. And typically this is at 30 degrees vertically and 10 degrees laterally. All right, vertically and also laterally. So in order to form a collimated beam, for example, in fiber optics, you need to have a collimated beam. You need to use a lens so that the light remains, it doesn't diffract or it doesn't diverge. Okay, because when it diverges, power is lost and intensity reduces. If a circular beam is required, cylindrical lenses and other optics are used. For single spatial mode lasers, using asymmetrical lenses, the collimated beam ends up being elliptical in shape due to the difference in the vertical and also the lateral divergences. Okay. All right, laser diode types. Simple laser diodes require high power and can usually be operated only in the pulsed mode. Okay, and you can see, as I mentioned just now, the light changes due to changes in temperature. Okay, so temperature has an effect on the wavelength, the emission wavelength of light. So that's why it is very important to have a cooling system for laser systems. Okay, so you have a TEC cooler and so forth. This is for high powered lasers. Okay, modification of a simple PN is a PIN, where you have an I region, an intrinsic region. And the purpose of this intrinsic region is simply to form a region where there can be high electrical field. Okay, so when you have active region which are undoped, you have fewer impurities, so you have lower non-radiative recombination rate. Therefore, you have lower threshold current. So if this region is undoped, you're going to have lower threshold current, okay, because there's not much impurity. And this shows the band gap, this shows the refractive index, and this shows the electric field. You can see that the band gap is low in the active region. The refractive index is high for optical confinement. This is for electrons and holes confinement. And this is the electric field for high electric field formation, so that light can be emitted out. Okay. So just a larger view. All right. So this is for carrier confinement, low band gap energy for recombination to occur. Carrier confinement, this is high refractive index material in the eye region, so that emitted photon stays within this region, and therefore you can have a high electric field because of high electrons and hole present here. Okay, so else then PN, PIN, we can also have double heterojunction lasers. So we add another heterojunction. Just now you only have A and B. Now you have A, B, B, A. You can add more heterojunction layers. So you have low bandgap material sandwiched between high bandgap materials. So for example, it's gallium arsenide with aluminum gallium arsenide, and it's called a heterostructure. In this case, it's called DH laser or double heterostructure laser. Okay, it is like a basic laser. So you have free electrons and holes. They exist simultaneously, confined in the thin middle layer. This also means that you can have more electron and hole pairs contributing to the amplification, and fewer are left out in purely amplifying periphery. So in addition, light is reflected from the heterojunction and is confined to the region where the amplification takes place. Okay, so if the middle layer is made thin enough, it acts as a quantum well, all right? And the efficiency of the quantum well laser is greater than that of the bulk laser, because the density of states function of electrons in the quantum well system, it has an abrupt edge. I will explain this in another slide, okay? Okay, so we have here what we call a laser containing multiple quantum well. All right, so this is MQW, multiple quantum well in the active region. So what happens here, you have a sea of quantum wire or a quantum dot or a quantum well, and you can improve the laser efficiency. Okay, so in a quantum cascade laser, the difference between quantum well energy levels is used for laser transition. So over here, there are about, I think, a number of quantum wells over here in order to get the laser emission over here. Okay. So the other structure is separate confinement heterostructure laser. Okay, so you see the problem with the thin layer, it is too small to effectively confine the light. So to compensate, another 2 layers are added on outside the first 3. All right, so there is a quantum well over here. You have material C or material A and B added on, and these layers have a lower refractive index than the center layers and confine the light effectively. So almost all commercial laser diodes since the 1990s, they have been using SEH quantum well diodes. So the confinement, optical confinement occurs in another layer, and the recombination occurs in another layer. You can separate it out. Okay. Else then, just now we looked at vertical structure. We can also etch out, or we can disallow the adjacent region from taking part in the electron hole combination and also the photon confinement. So by having this etched MESA, we etch out these adjacent regions. You can have excellent lateral carrier confinement, because there's only very limited region for electrons and holes to move. And also when the light is emitted, also it has got very limited region to move around. Okay, so it gives excellent lateral carrier confinement and also light confinement both. Okay, so this is the effect of using a quantum well, quantum wire, and quantum dot. Okay, this is density of states versus the energy. In a particular material, if you are using bulk material, Okay, this is the density of states in blue. When you change it to a quantum well, you are reducing two-dimensional of carrier movement, which is let's say y and z, and you only have x movement. Okay, so it's 2D, they only can move two-dimensional. So you can see that the density of states, the energy is following the red line over here. You have more control over the energy states. And when you use quantum wire, you can see it becomes more discrete. The energy density of states becomes more discrete. You can control the energy value of the material when you use quantum wire. The best is to use quantum dots because you have discrete power values, discrete energy values. You see, a single value. Whereas for a bulk state, you can see that it's varying. It's very hard to control the energy value because the density of states changes so much. So that's why using quantum dots greatly increases efficiency, simply because you can control the energy level of the material used. Okay. Okay, just now we looked at D equals to 1 micron. So in a quantum well laser, this D value is about 0.1 micron. All right. And again, using the same equation, just now we used 1 micron and the current is 10 kiloampere per centimeter squared. Shwinta, don't disturb Mama, please. Okay. So the diffusion length is 1 micron. And then if you pick 0.1 micron, the current density becomes 1 kiloampere per centimeter squared. What if you pick 0.01 micron, which is 10 nanoamperes, all right, or 10 nanometers? So you get a quantum well, but it is at the expense of a lower current, right? So what we do is we use quantum wells. We increase the number of wells. Instead of one well, you have multiple wells. So you can see that the intensity increases when you use multiple quantum wells. So for single quantum well, the emission intensity is limited by carrier capture into the well. So we replace that by using multiple quantum wells. Okay. This is another type of laser structure, which is the graded index separate confinement heterostructure. And in here, the single quantum well is very thin, so you have poor optical confinement. So we use multiple quantum well. But by varying the quantum well width, you can have various emission wavelengths. So if you want multiple emission wavelengths, we can use this kind of laser, which is a green SEH laser. Okay, so that's it for lasers. I've covered LED and lasers. Any questions? Hello?
Clear, Doctor.
All clear?
All clear.
So, so far we looked at electrons and holes recombining to emit light. Now we are going to look at detectors where materials absorb light to make electrons and holes. Okay, it's the opposite reaction now. Okay, no questions? Okay, I'll move on. We have another 30 minutes before class ends. Okay, so for light detector,
Can I ask you a question?
Yes, sure. Please.
Can I ask you a question?
Yes, Sivanathan. Yes, please.
How do you compare the efficiency of the quantum well of laser and LED?
How do you compare the quantum efficiency of
the laser and LED?
Okay. Okay. You see, LED, it is using a broad. If you look at the spectrum, you see, in terms of efficiency, you mean efficiency of conversion, right? Electrons and holes converted to light, right? Sivanathan, is that your question?
Yeah, IQE. Yeah, IQE, quantum, internal quantum efficiency.
Okay. So you see, if you look at this figure over here, in lasers, the efficiency is very high because you are using single mode, only one particular wavelength. Okay, only one particular wavelength. And in a LED, you have a broad wavelength because LED is using the light is spontaneous emission, right? It is not stimulated. It is a spontaneous emission, and that's why the efficiency, if you compare apple to apple, you give it same amount of power, you compare apple to apple, the efficiency in a laser is higher compared to an LED. All right. But you also need to look at other factors, right? Suppose everything is the same material, the same structure, the quantum well is same length, using same material, everything is the same. The efficiency, the internal quantum efficiency will be higher for a laser simply because it is a stimulated emission, right? You force the electrons and holes to move to a higher energy level to form the recombination. So in terms of a LED, the internal quantum efficiency is determined by spontaneous emission. It's very hard to control. It's spontaneous, right? You cannot control it. Whereas for a stimulated emission, you can control about the amount of power that you supply it with.
Understood, doctor. Thank you.
Yeah. I wanted to show you the so internal quantum efficiency simply means how much you see one electron hole pair recombine and form one photon. So you call it as 100% efficiency. But what happens is normally not all electrons and holes they recombine to form one photon. Some of the electrons and holes they may scatter and they do not recombine. So each electron and hole pair do not form one photon. So in that case, the quantum efficiency will be lower. Also in LED, you find that in lasers there are many confinement structures that can be done. All right. In a LED, this kind of confinement structures are not there, right? Because it's spontaneous emission. All right, it's spontaneous. It depends on the material, totally dependent on the material, the quality of the material used. So you cannot determine that each electron hole pair will form one photon. Whereas in a laser, you looked at the different confinement structures. You have carrier confinement and you have photon confinement. So these confinement structures make sure that the efficiency is high, both the internal quantum efficiency and also the external quantum efficiency, because you can control the electrons and holes to meet in the active region to emit one photon or to emit two photon and so forth. Okay? Okay,
Thank you, doctor. Yep.
Okay.
Yep.
All right. Let's move on to light detectors. So basically, I will cover photomultipliers, photoresistors, photodiodes, including avalanche photodiodes and also phototransistors. So these are all two-terminal devices. Phototransistor is a three-terminal device. Okay, that's the difference. So all of them are using effect of light. So now we are doing the reverse. Light is absorbed to get electron hole pairs. Okay, the reverse. Okay, photomultiplier tubes, they are extremely sensitive detectors of light in the ultraviolet, visible and near infrared. So they multiply the signal produced by incident light by as much as 10 to the power of 8, allowing single photons can be resolved. So the combination of high gain, low noise, high frequency response and large area of collection. So these are the typical applications: nuclear and particle physics, astronomy, medical imaging. So basically you have light coming in from here. You have a scintillator here. It absorbs the high energy electromagnetic or charged particle radiation. Then in response, fluoresces the photons at a characteristic longer wavelength and releasing the previously absorbed energy. So basically it absorbs the light and it sends it through this photocathode. And you can see that the electrons and holes, they move along these diodes. So these diodes, they have electrical or they have a voltage higher than each other. So the electrons and holes are moved further and further along the photomultiplier tube, and finally they reach to the electrical connectors. So it is able to detect very small amount of photons because there is an amplification of the electrons and holes over here. Okay. So it's a bunch of explanation. I think you can take some time and read through to understand further. Okay, basically it's whatever I explained just now. Okay. So finally, the photon, the accumulation of charge, it results in a sharp current pulse indicating the arrival of a photon at the photocathode. Okay, so this is a diagram of a photomultiplier tube. So it requires about 1000 to 2000 volts for proper operation. Okay, and can read through. All right. So normally, as mentioned just now, it's used in nuclear and particle physics, astronomy, and also in medical imaging. All right, you can Google and find out the exact applications. Okay. And photoresistors, these are also called light-dependent resistors. So it's a very simple concept. So in dark, the resistance is very high. With the presence of light, maybe in the daytime or when there is sunlight, the resistance drops. Okay. So this light-dependent resistor, so the resistance decreases with increasing incident light intensity, and it is made of high resistance semiconductor. So the resulting free electron and its hole partner, they conduct electricity, thereby lowering the resistance. So you have electron and hole pair flowing, so resistance reduces. All right. And okay, a photoelectric device, it can be either intrinsic or extrinsic. Intrinsic semiconductor, it has its own charge carriers, for example, silicon. And the only available electrons are in the valence band, and the photon must have enough energy to excite the electron across the entire band gap. So extrinsic devices, you have impurities added, p-type or n-type, okay? And the electrons don't have to jump so far, and lower energy photons are sufficient to trigger the device. So if a sample of silicon, it has some impurity, for example, phosphorus, so there will be extra electrons available for conduction. So this may be extended into visible range. So similar like lasers, we can provide impurity to the semiconductor in order to reduce the band gap that the photons, that the electrons and holes need to cover, right? So you can add this impurity, right? This is n-type and p-type, so it changes the band gap. Photodiodes. All right, photodiode is a type of photodetector. It's capable of converting light into either current or voltage depending on the mode of operation. So you can see that this is the surface of a photodiode. The surface is the one which will collect the light, and the light will stimulate the formation of electrons and holes, which will flow as an external current. Okay. And similar like lasers, you also have positive intrinsic and negative junction. All right, also PN junctions. Okay, and the window is exposed, or this part can be packaged into a fiber optic. All right, to allow light to reach the sensitive part. Okay, so basically it's a PN junction. So light hits the intrinsic region, and you have electrons and holes formed, and they move along the external circuit to form electricity or current. So the same similar equation is used. All right. And when a photon of sufficient energy strikes the diode, all right, which is at the intrinsic region, it excites an electron, thereby creating a mobile electron and a positively charged electron hole. So you have a electron here and a mobile hole over here. So it occurs in the junction's depletion region, or one diffusion length away from it. These carriers are swept from the junction by the built-in field of the depletion region. So because of a strong electric field here, this electron and this hole, they will flow through the external circuit. The holes will move towards the anode, and the electrons will move towards the cathode, and you have photocurrent flowing inside the device. Okay, so this is for Dilip, right? Who is the student from Surrey? There's one student from Surrey, Dilip Kumar, right? You are doing solar cells. So your solar cell is what we call photovoltaic mode. So when there's no voltage applied, zero bias, we call it photovoltaic mode. So the flow of photocurrent out of the device is restricted and a voltage builds up. So the diode becomes forward biased and dark current begins to flow across the junction in the direction opposite to the photocurrent. So this mode is responsible for the photovoltaic effect, which is the basis for solar cell. All right. So you can see that light is absorbed. So you have a hole over here and electron over here, and the electron flows in the external circuit, and you have solar cell formed, and this current can be used to charge up your phone, your car, or your water heater, and so forth. Okay, so I'm not sure what's the maximum efficiency for solar cell now. It states here as 32%. All right. So again, Sivanathan, you asked the question of internal quantum efficiency. So similar for detectors, you also have a quantum efficiency. One photon is supposed to produce one electron and hole pair. All right. So if you see here 32%, that means only 32% of electron and holes of 32% of light was converted into electron hole pairs. The remaining 68% is lost as heat or some other forms of energy. Okay, so this is in terms of efficiency.
Doctor, I have a question.
Yes, please. Yes.
The previous slide, you mentioned the maximum efficiency given by 32%. Is that a theoretical calculation or is actually experimental result?
Okay. For this, I'm not sure. I took it from which slide, but what I know is current solar cells, the efficiency is about 30%. These are, if I'm not mistaken, the first generation. Maybe Dilip, you know better than me. I think it's not perovskite. Perovskite is lower than 20%, but this is not theoretical. This is the actual efficiency. It's not more than 30%, Sivanathan, for solar cells. What I know, all right.
Doctor, actually the efficiency depends on the material that we use, right?
It's also dependent on the material that you use. Yes, correct. Yeah, whether it's a first generation, is using thin film or is using perovskite, right?
Yeah.
It dependent on the active material as well.
Actually, it's quite different because I'm doing dye sensitized solar cells. So
yes.
For
Yes, go on, Aimee.
is it possible to emit light through the anode or cathode?
You are doing dye synthesized solar cell, right? You're doing solar cell, right?
Yeah.
Okay, so you're doing a solar cell.
The light should be emit to the electrode or cathode. Anode or cathode.
The light should be absorbed, right?
Yeah.
The light is absorbed. Normally, your topmost layer in a solar cell is the P, right? The P layer, right? And your P layer is made thin so that the light do not have to travel far to reach the active region, which is your dye, right? But in solar cells, you can have both. You can have top illumination and you can also have bottom illumination. You can have both. You can have both.
Okay.
Right? But you need to look at the thickness of your material because you need to look at your light, the wavelength of your light. You need to look at the energy of the light and also the energy of the materials that you're using. So you need to check the amount of energy absorbed from the top or from the bottom, because if it's from the bottom, there are more layers that you need to go through, right?
Oh, so it's okay if we can put the light through the anode or cathode lah. Vice versa.
You can have both.
Okay.
You can have top illumination or bottom illumination. It's fine, but you need to check whether the light can reach the active layer or not. The light must be able to reach the active layer because different materials have different band gaps, and you must make sure that the light can pass through all the different band gaps, right?
All
You must ensure there's a flow. You must ensure the light reach the active region.
Alright. Noted,
Yeah.
noted.
Then only,
Okay,
then
thank you,
only it
Doctor.
can be absorbed. Then only it can be absorbed, right?
Oh, yeah.
Mhm.
Okay, thank you, Doctor.
Okay, so Dilip has mentioned here that the efficiency for perovskite solar cell is 25.7% currently. This is experimental, right, Dilip? Yeah, I think it's experimental. Okay. Yes, yeah, it's experimental. Okay. So let's move on. Okay. So so this is 32% depending on the material, yes, depending on the technology, whether perovskite or dye sensitized or thin film and so forth, depending on the technology used in the solar cell. Okay. So photoconductive mode, it is always reverse bias, all right, versus photovoltaic is forward bias. So it increases the depletion layer, it decreases the junction capacitance, it results in faster response times. So the reverse bias induces only a small amount of current. We call it as a saturation or a back current or a dark current along its direction, while the photocurrent remains virtually the same. So although the photoconductive mode is faster, the photovoltaic mode solar cells, they have less electronic noise. Okay. So this is a summary of the IV curve. All right. This is current versus voltage. Okay. You have 4 quarters over here. If you are using lasers, it will be the first quarter, photoemissive mode. When current increases or when the voltage is increased, you have increase in the current. This is the photoconductive mode for photodetectors, which is in reverse bias. You supply a reverse bias current and you can see when there is increment of light intensity, there is an increment in the current, right? Electron hole pairs, they form an external current which directly coincides with the amount of light absorbed.
Excuse
And
me,
this is
doctor, we
for,
can't see your slide.
oh really? I'm so sorry. What happened? Okay, I stopped sharing or what?
I can see the slide, Doctor.
Oh, okay.
I think some of them.
So Sivanathan, you can't see?
No, I can see the slide also, Doctor.
Sivanathan, can you see or not?
Now can, doctor. Now can, yes.
Okay. All right. Okay.
It disappeared again.
Okay. Is it your connection or okay? But you can talk, right?
Now I can see
Now you can see. Okay.
the
Okay.
IV curve. Yeah.
All right. The IV curve. So this is for laser diodes, photoemissive mode. This is for photoconductive mode, reverse bias, reverse voltage, and this is for photovoltaic mode, solar cells, where you have forward bias, and you can see increment in the intensity of light increases both the VOC, the open circuit voltage, and also the short circuit current. Right. So this is a summary of IV curve for different types of optical devices. Okay, now we move on to 3-terminal device, which is a phototransistor. So previously were all 2-terminal devices. So it consists of a photodiode with an internal gain, and it's a bipolar transistor. It is encased in a transparent case, so light can reach the base collector junction. So the electrons that are generated by photons in the base collector junction are injected into the base, and this current is amplified by the transistor operation. So although phototransistors have a higher responsivity for light, they are unable to detect low levels of light any better than photodiodes. Phototransistors have also slower, I'm not sure what's that word there. Slower what? I don't know. I can't see the slide underneath it. It's been blocked. Slower response time. Okay. All right. So the material used to make a photodiode is critical. So similar like lasers and LEDs, different materials for different wavelength range. But the difference with lasers and LEDs is you can see the presence of silicon and germanium, because silicon and germanium, they can absorb light in this region, but they cannot emit light. Okay. And for this is for visible. All right. Silicon and germanium can be used for visible, and germanium can also be extended until infrared. Indium gallium arsenide for infrared, and lead sulfide also for infrared. Okay, so again, silicon, it is capable for detecting energy in the visible and also in the near IR, about 800, just below the visible light. Okay, again, some calculation just to show how do you change from a band gap of 1.11 electron volts. It corresponds to wavelength of 1115 nanometer. Just an example of how to convert the band gap, okay, to wavelength. All right, because of their greater band gap, silicon-based photodiodes, they generate less noise than germanium. But germanium photodiodes, they are mainly used for higher wavelengths, 1 micrometer. And since transistors and ICs in your phones, your laptops, your PC, they are all made from semiconductors and they all contain PN junctions, so almost every active component is actually a photodiode. So many components, especially those sensitive to small currents, they will not work correctly if they are illuminated due to the induced photocurrent. So you have to make sure that it's not exposed to too much of light. So in most components, this is not desired, so they are placed in an opaque housing. So dark housing, light cannot reach the components. Okay. So since housings are not completely opaque to X-ray and high energy radiation, so many IC can also malfunction due to induced photocurrents. Okay, so you cannot see X-rays and higher energy, right? So they can affect your electronic devices as well. Right, these are just some typical output parameter for photodetectors. So basically you have responsivity, how much of current is produced per watt of photon. All right, we call it ampere per watt responsivity. Also, you can express it as quantum efficiency, the number of photo-generated carriers, electrons and holes, to incident photons. You also have dark current when there is no light present. How much is the dark current or the saturation current? Okay, without the presence of light. Noise equivalent power is given by the detectivity. All right. So this is the minimum input optical power to generate the photocurrent. What is the minimum input optical power? What is the lowest power that can be detected? So this is for silicon. So you can see that the highest responsivity is at about at about 1000 or something, 900 something. All right, the highest responsivity. And this is the IV curve for dark. And with the presence of light or illumination, you can see that the curve is shifted lower because of the presence of the photocurrent. This is for reverse bias. Okay, and when it's used in optical communication, you need to look at the sensitivity because it affects the bit error ratio, the ones and the zero. So the minimum detectivity makes sure that the signal produced can differentiate between a positive signal, which is a 1, and a negative signal, which is 0, with light and without light. So with light, it will be 1, without light, it will be 0. So the sensitivity is important that it can switch between 1s and 0 very effectively. So similar to the laser, intrinsic region can be added to the PN junction to form a PIN. All right. So the function is the same. It is to increase the area for absorption of light. Okay, you can read through all this. So this is again the IV curve. All right. And this shows the effect of frequency on the photodiode. So high frequency resistance on the photodiode. So it can act also as a variable resistor. You can have high frequency resistance and it can range from a high resistance from 0.1 ohm to 10 kilo ohm. So the white intrinsic region means it will have low capacitance when reverse bias. So this shows the 3 dB frequency for different voltages, reverse bias of the device. So this is for 0, the blue is -2 and the green is for -4. You can see that the 3 dB wavelength increases when the input voltage or the reverse bias voltage is increased. This shows, remember I told you about the ones and zeros. So from 0, it goes up to 1, and then it's going down to 0. So in an optical communication system, this should occur at the correct timing, so that the signal can be differentiated for zeros and also for ones, right? The detectivity needs to be excellent. So this shows ones and zeros for different wavelengths, all right? Okay, I think you can read through. It's already 4, so I just like to rush through. So this is for photodetectors. Okay, so similar, I think I've explained all of this just now, just a repetition. So this shows the electron energy from high, and then it goes lower here. And you have the charge density at this region. And the electric field is very high over here, such that when photon hits this region, the electron hole pairs, they get accelerated to the junctions. Okay, and this is the total absorbed power, right, at x, at a distance of x inside here, right? So at the surface it's highest, P naught, and then as you go down, this power decreases. Okay. Avalanche photodiode, basically avalanche photodiode has avalanche region. Okay, this region over here, what happens in this region is the electrons are drifted, and they experience a very high field, such that you have impact ionization. And for APD, the responsivity has a multiplication factor, M, right? That is for APD. This M is given by the current in multiplication format over the normal photocurrent. Okay, and so this is the difference compared to a normal photodetector. You have an avalanche region. Okay, so this shows different materials for the APDs which can be used. Okay, for next 5 minutes, I will just go through some recent works which is related to lasers, LEDs, and photodetectors. So it will take me about 5 minutes, and then we're done with the class. My apologies for the delay. It's already 4. Okay. Okay. All right. How many devices or gadgets that each of you have? So this figure is from I think 2018 or 19, where it shows the world population. All right, you have billions of devices over here, and this is the year. So this is 2020, and it shows that each one person, they will have 6 things online. You will have a sensor, smart object, device clustered systems. All these objects is projected in 2020. So you can see that the amount of connected devices are increasing, right? Although the world population is not increasing such as that. So therefore, what is required is devices with small form factors, higher speed, and higher sensitivity. So I hope all of you are aware of the Internet of Things, Internet of Me, Internet of Everything, Big Data, Industry Revolution 4.0, which is based on cyber physical systems. So IR 4.0 requires everything to be connected with many, many devices. So as research students, you need to aim to make devices with small form factors with higher speed and high sensitivity. Okay, so in optoelectronics market snapshot, it shows that LEDs and CMOS image sensor, this is the percent share, and this is the CAGR, which is like economical percentage of return on investment. Okay, CMOS image sensor and fiber optic are based on based laser transmitters. They have the largest market share, right? LED and CMOS image sensor normally used in television and so forth. Okay, so others are like other optoelectronics, displays, and so forth. Okay, so this is from 2014 to 2019. So it's a big market over here. All right, lasers can be combined to form what we call optoelectronic integrated circuits. So you have a laser and you have a waveguide over here. You have optical fiber to take the light out, and you have a photodetector over here. So lasers and photodetectors can be used in integrated circuits. So you have LED, VCSEL, LD to be used as the source, and you have a sensing area, which is an on-chip modulator over here. It can be SPR, micro-ring resonator, or Mach-Zehnder interferometer, and also you have a detector over here. So this is the fabricated device. Is using a dye laser with waveguides, a cuvette to sense different kinds of molecules, and also a photodiode. All right, so these are actual research papers. Okay, this is another example. It's a graphene-based optoelectronics for transmission. So basically, it's using LED and also OLED. Also using energy harvesting, for example, dye-sensitized solar cells and also solar cells. Okay, and detection is using photodetector in a lab-on-chip application. All right, you can read through on your own. This is an organic solar cell. This is a dye-sensitized solar cell, and inorganic, organic, dye-sensitized solar cell. And this just shows the schematics of the organic LED and the photodetector, right, which is using graphene. Okay, so we can also combine optoelectronics with MEMS, which is micro optoelectromechanical based label-free biosensor. So basically you have a deformable membrane over here, and when light hits this region, you can have a change, a deflection of the transmittance of light, because the membrane changes, and the presence of light and different kind of absorbed molecules, it interferes with the Fabry-Perot interferometer, and the detection is done by a silicon on insulator based photodiode. Okay, this is an example of a research paper. Also using surface plasmon resonance, this is for point of care applications. So basically you have a LED light over here, you have a plasmonic chip over here, and this is a CMOS circuitry. So this is the plasmonic substrate, which is comprised of gold and also silicon nitride with an adhesive layer of titanium. So this is for detection of protein, and the black line shows the bare transmission, and after binding there's a shift in the transmission signal. So for the bare, intensity is very high, and after binding of the molecules at the gold layer, you have a decrease in the intensity. All right, so it is covered by protein, so it reduces the intensity of light. So this is an example of SPR based point of care application sensor. Plasmonic laser and laser arrays using nanometallic structures with zinc oxide nanowires for lasing at 372. So this is lasing at 372 over here, the blue color, all right, with the input power of 87 megawatt. So you have, this is the zinc oxide nano wire, okay, over here, and you have, this is the cross section of it, and you have light emitting out from this nanostructure, okay. So it just shows the schematic of the structure. Plasmonic photodetectors. So this is using a high-speed, it is a high-speed photodetector using a germanium core, right? The active region is germanium core, and it has a cladding of gold on a silicon optical waveguide. All right, so the amount of quantum efficiency, internal quantum efficiency of 36%, and the photo detection is up to 100 gigabit per second. So it's for very high frequency optical communication application, right? New materials. This is germanium stannum on SOI. The speed is 20 gigabit per second. It's operating in mid-infrared region, which is at 2 micrometer. So the dark current, all right, this is current versus the voltage. Dark current is in reverse bias, and upon illumination, you can see that there's an increase in the photocurrent. So it is using a waveguide and oxide window over here, all right. And this shows the wavelength variation from 1.9 micron up to 2.5 micron for two different voltages. Okay, so higher voltage, of course, it gives higher current. Graphene-based photodiodes, if any of you are working on graphene, so graphene can also be used to make photodiodes. It could replace germanium and InGaAs for long wavelength, multi-gigahertz speeds, small form factor. You can have 20,000 chips on 1 centimeter squared, and you can use a graphene silicon heterostructure for mid-infrared region. All right, perovskite solar cells. This is just showing the effect of nanoparticles on the efficiency of perovskite solar cells. So the first is a control. The sample number 1, it has got gold and titanium dioxide nanoparticles. This has got also the same nanoparticles, but it's suspended in the upper region, not at the bottom here. And the third sample, you have both in the upper and also the bottom region. And lastly, you have this P25 nanoparticle just as a control. So if you compare the efficiency, all right, of all the three samples, you can see that sample number 3 has got the highest, which is 18.24. So the presence of quantum dots, right, gold, titanium dioxide nanoparticles or quantum dots increases the efficiency of the device. And you can see that sample number 3, S3, has got the highest amount of current density compared to the rest. So usage of quantum dots to increase efficiency. All right, diode fiber for fabric-based optical communications. So basically, it shows how you can use lasers on the fiber optics. So this is using a blue laser, right, or a blue LED, light emitting and high bandwidth photo detecting fibers. So it can perform both emission and also detection. Okay, what is the application? So this is a shirt. It is a shirt. It has got both the transmitter and also the detector. So this is the LED. It transmits light, and this is the detector. So how does it work? Is it can detect your PPG, right? The pulse. All right, it can detect your pulse. So light is emitted out, and the emitted light will detect or will interact with your pulse or your pressure of your blood, and it can form what we call a PPG signal over here with the presence of a function generator. Okay, so this is a light emitting and a light detecting fabric. So it can be used for point of care. If you have a patient with a heart problem or some medical condition, you can make them wear this kind of clothes to constantly detect their heart signal and so forth. So this is application of transmitter and detector on fabrics. Okay. All right, that's the end of my lecture. All right, I'm sorry I took up an additional 13 minutes. Do you have any questions? But since it's late, you can email me, all right, at my email. Or you can WhatsApp me. My phone number is in Folio. And if you don't understand any part, feel free to ask me. If I know, I'll answer. If I don't know, I'll look for the answer for you. Okay, so there is also an assignment for this class. Okay, and it's quite straightforward. It's just you need to do a one-page. Wait, let me go back here. Where's my desktop? It is already in Folio. I'm not sure if you managed to. Okay. Right. So this is your assignment. It is a very simple assignment. If all of you are doing something related to optoelectronics, you can just write something related to your work. If it's not, then you need to look for something which is related to optoelectronics. So basically, it is very straightforward. Write a short review about micro or nanoscale optoelectronics device, 500 words or maximum 1 page, and email to me before 30th of December. So you can choose from these 3 topics: recent developments of nano optoelectronic devices, potential applications, methods in fabricating. All right, so you can choose. So if your research work, if your current master's or PhD research work is related to nano optoelectronic devices, you can just use your proposal and use your literature review and so forth, but you have to make it to 1 page, summarize it to 1 page, put in a few examples of past work that is related to nano optoelectronic devices. Okay, and this is individual assignment. So you have about 1.5 months. You can submit. Please submit through UKM folio, right? Because it needs to be online, not email, right? This is a mistake. You need to send it through UKM folio, right? Okay, everyone.
Okay.
Okay, Doktor.
Are you clear about the assignment?
Okay.
Right. Thank you so much for listening.
Thank you,
And
Doktor.
if you have any questions, please email me. Please email. Or you can WhatsApp me at 016-360-8970. Okay, I'll be happy to answer questions if you have anything about the lecture. All right, thank you so much for joining. All right, sorry I took up extra time. Stay safe, stay healthy. Bye-bye, everyone.
Okay, Doktor.
Bye-bye.
Thank you, Doktor.
Bye-bye. Okay, I'll end the class, all right? Okay, bye.
Yes, please.